Welcome students to the next lecture on the statistics. Today we will discuss about type 1 and the type 2 error. Myself Dr. Gar, working in the School of Mathematics, Thapar Institute, India. So before starting the what is the type 1 and the type 2, let's discuss some examples which will help you to motivate in this topic. Say you have decided to get tested for the COVID-19 based on some mild symptoms like headache, fever, cough and so on. What will happen once you will get the tested for the COVID-19? Then the result may be the test result you have a coronavirus, but you actually don't have. Similarly, the test could result say that you don't have any coronavirus, but you actually do have. What is the meaning of these two cases are there? In both the cases, you have observed that there is something an error in it, because the results say you have the coronavirus, but you actually don't have. And on the second case, the results say you don't have a coronavirus, but you actually do have. It means there is some error inside it. Look at one more example. So a failed candidate is passed by the teacher. Then once the failed candidate is passed by the teacher, then definitely the student face will be like of here. Is it there any error inside it? Then you can see in both the examples, again it's a failed candidate, but it's a pass by the teacher. So is there any error in both the examples? Yes, there is an error inside this both the examples. So whenever there is an error in terms of the statistics, then we have to study for the type 1 and the type 2 errors. What are the type 1 and the type 2 errors? So let's say you have the null hypothesis H0 and the H1. What is the meaning of the null hypothesis are there? Say this man will try to impress this beautiful lady or beautiful girl, and he propose him with like say, will you marry me? Then what are their options for this girl are there? Whether he can rejected his proposal or they can accepted his proposal. That is, whether they can rejected them or they can fail to reject it. It means they will accepted their proposal. So what will happen if they accepted their proposal? That person will be very happy. On the other hand, if she will rejected the proposal of this, that is, she will rejected their null hypothesis, that is H0, then we could try to find what are the possible reasons behind that. So there may be the two reasons behind that. It may be there is really a difference in the populations, or population is there is a difference between their natures of these persons and the mentality of these two male and females are there, or otherwise it is possible that there is no difference in the population. But if you look about the first case, if there could be really a difference in the population, then definitely you will reject it there, because there is a difference between the two different kinds are there, then definitely there is a correct decision to reject the hypothesis. On the other hand, if there is no difference between the populations like of here, if there is no difference between them, then on what basis you have rejected the H0? Then the question arises is, once they are almost similar, then on what basis you rejected the H0? It means on what basis, that is H0 is my true, but you still rejected the H0. It means there is some error inside it, and that error may be that the sample will be different due to the sampling variation and so on. So it means there is a correct decision, but here there is an error inside it. Or in other words, we made an error in that case. So let's say, in order to understand it more clearly, let's say the reality is H0 is 2, and finally you made a decision as rejected H0. What is the meaning of that? It means initially H0 is correct, and finally you have made the rejected them. What is the meaning of that? There is an error inside it. Why? Because H0 is initially 2, but you still rejected them. Look at the second case. H0 is false and you rejected the H0. It means there is no error inside it. That's a correct statement. Similarly, once you will fail to rejected the H0 and H0 is 2, fail to rejected H0 means you may accepted the H0. So once H0 is 2, then you may accepted that. It means there is a correct decision. And similarly for the last case, there is an error inside it, because you accepted the H0, but initially H0 is my wrong. Now there are the two errors are there. These errors corresponding to the types of the error we will call as the type 1 and the type 2. Like type 1 will give you the false positive conclusion. Look at that. Initial, this is the correct statement, but your decision is to be rejected. It means you give the false decision on the correct conclusion. Similarly, the type 2 error is means you have to accepted them. Which one is accepted? The false statement, that is a false negative conclusion. Look at the same example related to the COVID-19. So you have the two kinds of the error. One is a false positive and the negative. False positive is that when the results say you have the coronavirus, but actually you don't have. What is the meaning of that? You have the false positive result. On the other hand, if you don't have a coronavirus, but actually you actually do has, that means again that there is an error we call as the type 2 error. Similarly, a failed candidate is passed by the teacher. What is the meaning of that? A failed candidate passed by teacher. What is the error of this? That is, it will give you a false negative error. That's this is corresponding to type 2 error. Or you can say the error of rejecting the H0 when it is a true is called as the type 1 error. The error of accepting the H0 when it is a false is called as the type 2 error. The probabilities corresponding to the type 1 and type 2 error is denoted by alpha and beta. That is, alpha is rejecting H0 provided H0 is my true, and beta is accepting the H0 when it is a false is my here. So you have to remember this definition for the example that we will see in this presentation too. Now say you have the reason are there where I can write the rejected decision, the right hand side, fail to rejected here. The value which divide this is called as the critical value, that is which divides the rejection reason and the acceptance reason. This is my acceptance reason and this is my rejection reason are there. This critical reason is denoted by W and acceptance reason is denoted as W complement P. So this value is called as the critical value, and the reason is called as the critical reason. For example, if you draw the hypothesis H0 and you can say this is my rejection portion, so this value is called as my critical reason, or you can say this is my W. Now this is my H0, you have to rejected H0, this is my rejected portion, this is my rejected H0, this is my accepted H0. So you have to rejected H0 provided it is true, then it is called as the alpha, that is a type 1 error. Then we can write this value as, that is a probability of critical reason, that is X belong to the critical reason provided H0 is true. How you can find this area? That is nothing but the integration of the f of x dx, where fx is the PDF of the distribution I call as the L0. L0 is the likelihood function when you have the more than one samples here. On the other hand, once you define the H1, that is a null hypothesis, then you have to accepted the H0. This is my accept H0. Then the reason is here called as the beta, that is called as the type 2 error. That is whenever it lies in the critical not critical reason, that is accepted reason W complement, when H1 is my false. Again you can write this value as of integration I call as the L1 corresponding to the H1, where L1 is the likelihood function. Again this value is the alpha, this is 1, and this is nothing but my 1 minus beta. Also we know that the critical reason and the non-critical reason, the total area is my 1. Now you can know this, what is the value of this is, this value is nothing but my beta, so I can substitute this value as a beta and then I can find this value as here, that is the value which lies in the critical reason provided H1 is my true, that is of this portion, that is which I highlighted as this green color here. So this value is my 1 minus beta. So remember that accepting and the rejecting are there. Now based on this alpha and beta, you have defined the level of significance and the power of the test. Level of significance is denoted by alpha, which is nothing but the probability of the type 1 error, while it is defined as rejecting of this when H0 is true. Power of the test is called as the 1 minus beta, that is called as the power function, and it is defined here where beta is this one, so 1 minus beta is nothing but my here. All of you know that alpha I have defined like this way. It is also called as the size of the critical reason, and in this power of the test, the value of the power function at the particular point means for the particular value of the x is called as the power of the test R. How we can solve this one? So we will see a couple of the examples, but if you are working on the quality controls, then this type 1 and the type 2 error is called as the production risk or the consumer risk are there. So let's say we will discuss about these 6 examples so that you may able to understand in a very shortcut tricks as well as simple manner. Say you have some probability density function here. You have to test the hypothesis H0 against the H1 by means of the single observation. So it means this is my single observation. What will be the size of the type 1 and type 2? It means your target is to find the value of alpha and beta is there by choosing the critical region as this and this. Also obtain the power function. So power function is 1 minus beta. So once you know beta, we can compute 1 minus. The approach is very simple. How you can solve that? So we can start from here. This is the PDF. It's a single function. Let's start with the first part, that is x is greater than or. So I will try to here. Critical region is given to you. So I call it, you can see that this, what would the size if this as my critical region. So whenever the critical region is given to you, you can consider as a W. Now since it is a, what is the size of this is a single observation. So it means my likelihood function is I varies from 1 to 1. So I varies from 1 to 1 is nothing but my same function. So I denote it as here. Now once you are defining the W, you can compute as a W complement. What is the opposite of this? It is nothing but my less than. Now our target is to find the value of alpha and the value of beta. So we can apply the definition of alpha and beta. I can substitute the value here. X belongs to W, like say X belongs to the greater than of this. What is the H0 is my? H0 is theta is 1. Now you can see here how you can solve that. This is the integration of the L. What is the L is 1 by theta. So I can write this one value of 1 by theta of this. Now integration is X varies from 0 to theta. This is a 0.5. So can I write this value as 0.5 to this when of this? That's true. Now you can integrate that theta is 1. So this value is my 1. So you can integrate from 0.5 to 1. What is the f of x is 1 upon theta. Theta is my 1. So this is my integration of here. Now after solving, you will get this value as level of significance. Same for here. Now what is the value of the W complement? You have to write here. You can write this. Again you have to express this in terms of here. So this is the upper bound is given to you. So I can write this value as lower bound of here. Now theta is my 2. So what is that? This is from 0 to 0.5. The value of theta is my 2 over this value. So this is the integration of this. You will get this answer here. Now how you define the power of the test? The power is nothing but 1 minus beta. So this is the answer of the first part. Now we can do the same procedure for the rest of examples as well as for this second part. Now in this case, this is my critical region. So I consider this as my W. What is the opposite of this is? W bar is all those are real line minus of this. Your target is to define the value of alpha and beta. What is that? Alpha x belongs to W like of here. So we can write like this way. Now since theta is my 1, so I can integrate this value from 0 to theta is my 1. So that is 0 to 1 and 1 to 1.5. So what is the value of the 0 to 1? So this is my here. This is my 1 to 5. So now you can integrate from 1 to 1.5 here. What is the theta is in this case is 1. So the integration of this is my 0 because this range lies in this side. So the value of this is my 0. What is the value of the here? This is r minus. So instead of this, I can write this as 1 minus of here. H1 is nothing but my theta 2. Now what is that? I can substitute the value of x belongs to W like of this. Now you can integrate this value. Now in this case, you can see theta is my 2. So this is my 2. I can write this value as from 1 to 1.5 of 1 by 2 because 1 to 1.5 now lies in this case. So what is the answer of this is there. So you can see this one is the right answer. Similarly, you can find the power of the test. You can write like here. Now quickly move on the second example. It is given to you that critical region is my x is greater than equal to 1. So you can find the W bar, that is my here. H0 and H1 is given to be. Again, it is based on a single observation. So L is nothing but my same value is there. That is f of L. You have to find the value of the alpha and the beta. Again, we will apply the same approach. X belongs to W, it means x belongs to the here. What is that? X greater than 0. So I can write this as from 1 to infinity. F of x, that is my theta e raised to power of this. But theta is my 2. So I can replace this value as my 2. That is here. 2e of this. Now once you will integrate them, you will get this right answer. Similarly for here, when x belongs to the w complement, that is x is less than 1, you can see here, but x is greater than equal to 0, so it means you have to integrate from 0 to 1. What is the value of this is, when theta is my 1, so it is 1 e raised to power minus 1x. Now once you will integrate them, you will get the required answer as of here. Again, if you want to calculate the power of the test, then power of the test is nothing but 1 minus beta. So if you solve them, you will get the answer as 1 by e. Look at the another one is there. So let p is the probability of this. So single toss, h0 is given to you, h1 is given to you, the toss is 5 times are there. So h0 and h1 is given to you as 0.5 and 3 by 4. What is given to you? You have to toss the coin as a 5 times and record it as a head. So let x be the number of the heads. So do you know which one x follows? X follows my binomial distribution. Why? Because n is my 5 times, that is n is my finite. So it means this is my binomial distribution, and the PDF is my here. What is the critical reason is that? So it is rejected. So rejected, it means this is my critical reason when you have the more than 3 heads. It means critical is x is my number of the heads when more than 3. So x is greater than 3, w bar is my here. You have to define the value of the alpha, and you have to calculate 1 minus beta. This is your target. We can start from here. What is the value of the x belongs to w, that is x greater than 3. Now since it is a discrete, what is the value of the maximum is 5, so I can write this value as 4 and 5. Now I can substitute this value here by taking probability as 1 by 2. So 5c4, p is my half, 1 minus p is again half. After the calculation you will get this result. How you define the power of the test? It is nothing but 1 minus beta, so we need to compute firstly as a beta. X belongs to the w bar, that is x is less than equal to 3. How you can write that? This you can write this value as x is 0, x is 1, x is 2, 3, 4 and so on. Here you can see, or you can also write this value as 1 minus of 4 and 5. So since this calculation is much easier, now I can substitute this value here by taking p as my 3 by 4. So p is my 3 by 4, this is 1 by 4 and so on. So this is the answer of the beta. So therefore what is the value of the power of the test is 1 minus beta, so nothing but my is the required answer. Look at the another one is there. So it is a normal distribution is given to you, h0 is here, h1 is given to you based on the size of 10, and this is my critical reason. So you can see this is given to you. What is the opposite of this is my w. Now if you find the value of the alpha like of here, but here x is the collection of all those elements, so it is very difficult to you. So what you can do is, I can consider this value as my y. I will try, since x is my random samples of here, so it is my, since it is a random sample, so they are IID. So firstly we will try to find the mean and the variance of this y. That's very simple. We can find the mean of this, that is here. What is the e of x1, that is my mu. What is the e of x2, they are IID, so they are always same, plus of the 10 nu. So if you take the sum, you will get this answer as 55. How you find the variance of this? This is nothing but my variance of x1. 2 times means that is a 2 square of variance of this and so on. What is the variance of the x1 is nothing but my 4. Variance of x2 all are my IID, so it's a 4. So you can see right off here after the calculation of this. Therefore y is my, so what is your w? So this means w is nothing but my y greater than equal to 0. Why? You can see I consider this as my y, so this value is nothing but y is greater than equal to 0, and y complement is nothing but my here y is this. Now the rest of part is simple. We can start with the value of the alpha for this. How you can solve that? You can take y is nothing but this, h0 is nothing but mu is minus 1, here is plus 1. Once it's a normal distribution, you have to convert them into the z. Z is my here. Now this is for the y, so you have to consider this for the y are there. What is the value of the mu? Mean of the y is my 55. What is the standard deviation of this is my 1540. Corresponding to minus of 1, you can see this is minus 1, it is my plus 55. So after this solution, you will get this answer as here. How you find this? This is nothing but my CDF of the normal distribution, you can see from table 1.401, 1.4, 1.0. So you will get this value as here. So this is the value you can see from this table. So this is the value of this alpha. Similarly, we can start with the value of the beta. We can substitute this value in the z. Z is nothing but my y of here. Now corresponding to this, mu is my 1, so it is my here. Again you will get this value minus 1.405. You can take from the normal distribution table. This value is nothing but my here. So therefore the power of the test is nothing but my 1 minus beta. Look at the last example are here. Again you have to find the critical region. You have to find the significance value alpha. Power of the test is 1 minus beta, and this is the exponential distribution is given to you. This is given to you. Again we will take this value as my y, and we will try to find the normal distributions. What is given to you? Xi's are my exponential distribution with parameter here. Now this is not the normal distribution, but how you can find the distribution of here? We can try to find our target. If I consider this as my y, then our target firstly to find the distribution of this y. How you find the distribution of y? So that's a very simple. We can use the MGF function. So we can find the MGF of this, since they are the independent or identical, so you can take as a product. What is the MGF of the exponential distribution? We know that if x follows the exponential distribution with parameter here, then MGF will be this one. Now the parameter is my 1 by theta, so it means this value is my here. So this is here, this is here, so you can substitute this value, you will get as minus of 2. Now do you think that any of the distribution whose MGF will look like of here? Yes, this is the MGF of the chi-square distribution. If you compare them, you need this value as of 2, that is replacing this theta by the 2, but this theta is a parameter, you can't replace. If I replace the capital T to be my here, then can you say this value is same as of this? Yes. So you can use the property like of here, that is you can use this property, moment generating function of the Cx is nothing but here. So I can take C as my 2 by theta. So now if you substitute this value, you will get this expression as here. Now if you compare them, what is the value of the n by 2? That is my 2, that is n is my 4. What is the n is? In this case n is my degree of freedom. So therefore what you conclude that if x follows the exponential distribution, then this one follows the chi-square distribution with the parameter degree of freedom is 4. Now we all know that how we can solve that. So if we take y as of this, it means it follows of this one. So what is the critical region of this? So if I multiply this by 2 by theta on the both side, then the left hand side is my y, the opposite of this. Now the rest of part is similar. You have to do alpha. This is my critical. Now you can take value of this. Y w belongs to here, that is of this one. Theta is my 2, so it values 2 will be cancelled out. Y is my x chi-square. How you can find this value? You can start with the chi-square distribution table here. Look at the chi-square degree of freedom is 4. Look at the value of the 9.5. Which value is greater than of the 9.5? This value is not. This value is my greater than of this 9.5. So the corresponding value of alpha is my 0.025 is the required answer. Similarly, if you want to find the value of beta, you have to take from here. You can get the values of this. Now again you can take the values of the chi-square which is less than 14. So again take here, this is 16. If you extend the table, you will get the exact values of here. Once you know the value of the beta, you can easily find the power of the test like here. So this is the way you can solve the problem related to the type 1 and the type 2 errors. I hope you can simply learn from this. We will see the next lecture on the Newman-Pearson lemma and its proof with respect to their examples. Till then, you can simply follow this link for finding the various videos. Best of luck, students. Happy learning.